Now for some discussion of energy changes in reactions that we didn't have time to indulge in this semester due to the way the course lands, and how these things can be explained in terms of heat changes. How does the amount of heat relate to grams or moles? How do you represent it in reaction equations? If you've got the handout from class, it's right on there on, I believe we're on page 3. So, back up, page 2. So, model 1 has the formation of water, a reaction where you combine hydrogen with oxygen to make water, and heat is a product because it's an exothermic process. How much heat is released as a product? Well, it turns out that it's 123 kilocalories per mole. Well, what does that mean? It tells us it's 123 kilocalories released for 2 moles of hydrogen reacted, or 1 mole of oxygen reacted, or 2 moles of water produced. Those all go for 123 kilocalories of each amount, as shown with their stoichiometric coefficients in a balanced equation. The enthalpy change, delta H, is the symbol for that, is how we write these things. And so if it's an exothermic process, it's going to be a negative value of 123 kilocalories per mole. It's negative because it's exothermic. The heat is on the product side of that reaction. So you could legitimately write it the same in an equally meaningful way as saying 2 hydrogen gas with oxygen gas makes 2 water gas, and 123 kilocalorie is noted as a product because it is a product, it's released, and it's shown with a positive sign because everything in a reaction equation is just one thing after the next with positive signs. Everything has positive signs, but in the context of delta H, then is where you have a negative sign for an exothermic reaction. Now, what we have to be able to do is a little bit of calculation here, and it's problems like this on your homework similar. How much heat is released for 32 grams of oxygen? 32 grams of oxygen. Well, these things are per moles, and so we have to find out the moles of the oxygen. Well, 32 grams of oxygen, that was intended to be easy. 1 mole of oxygen is 32 grams of oxygen, and we just read up here at the top, it's 123 kilocalories for 1 mole of oxygen reacted. Oh, all right, so 1 mole of oxygen. Well, you about could have skipped that other step if you saw it, because this cancels, and this cancels, and the answer is 123 kilocalories. How much heat is released? There's no sign shown here, we're just telling how much. We don't put a sign plus or minus when we're asking how much. So far, so good. Let's keep going. If we could relate to amounts of oxygen, let's relate to amounts of hydrogen. So if you have 4 grams of hydrogen, well, it's again always per mole, so figure out the number of moles. Moles of hydrogen, 1 mole of hydrogen is more or less 2 grams, 2.02, which is fine for this purposes, 2 grams of hydrogen. And it tells us up here it's 2 moles of hydrogen corresponds to 123 kilocalories. Just put that in as a conversion tool, 123 kilocalories for 2 moles of hydrogen. Again, the moles of hydrogen cancel, the grams of hydrogen cancel. 4 divided by 2 is 2. So 2 times, oh, sorry, there's 2 on the bottom too. Uh-oh, so 4 and 2, well, that all cancels. So it's still 123 kilocalories, isn't it? So you had 2 moles of hydrogen, same amount of energy released. Very easily enough viewed. Next question then is going to be a little more interesting. We always have to have a more interesting example, don't we? How much heat is released for 72 grams of water? All right, so now I'm going to adjust my funny little symbols that don't compute when they're supposed to. 72 grams of water. Well, this is not going to be 1 mole or 2 moles, is it? So what's the molar mass of water? Well, think about water. 2 hydrogens is 2, 1 oxygen is 16, and once in a while this number looks familiar. 18 grams of water is a mole, and 72 divided by 18, you're not going to do it in your head, I know. And there's going to be 123 kilocalories for how much water? Well, let's go back and look. So it's 123 kilocalories for 2 moles of water. It comes back to our balanced equation right here. And put in your 2 moles of water. And Now we'll do some math. What's 18 times 2? That's 36. And 18 times 2 in the denominator goes into 72 twice. If you don't have your calculator, you can come up with that number, and you can do it with your calculator, either one. So 2 times 123 is 246 kilocalories. How about that? Not tricky. It just requires a little bit of mathematical manipulation. Those are examples of how you come up with kilocalories per mole. It's always per mole as stated in a balanced equation. In this case, the process was exothermic. Because heat is a product, you can list it either in the balanced equation like this, or separately as a value of delta H. Now, let's look at another example. The thermite reaction. We've perhaps seen this reaction on a video if you've viewed some of my other recordings. And the reaction of iron oxide, iron 3 oxide with aluminum to make aluminum oxide and liquid iron is, again, an exothermic process. The heat is shown here, and if you've seen that one, it's very, very exothermic. And so if 203 kilocalories are released for every mole of iron 3 oxide, there are two ways to represent this in the process. So either you put the heat in kilocalories in the following reaction equation, so you just add it in here. So put 203 kilocalories right alongside everything else in an equation with reactants and products and an arrow between them. Or option number 2 is to write the reaction showing the compounds as reactants and products and then just list heat separately as a delta H value. And so in this case, it's a 203 kilocalories, but remember this is exothermic, so that's very appropriately a negative sign. So every time that this reaction takes place, heat is always released. And we can determine how much there is for 27 grams of aluminum. If we remember, this is always per mole as shown. Per mole as shown in here. So aluminum is going to be for 2 moles of aluminum. So minus 203, oops, wait a minute, we forgot to do something. We forgot to calculate the moles. Okay, if you got your trusty periodic table, whoops, that didn't behave properly. Calculate the number of moles of aluminum. So 1 mole of aluminum, its molar mass, right off the periodic table, is 27 grams, close enough. So we got 1 mole here, and it's 203 kilocalories released per how many? Oh, like we just said, it's going to be for 2 moles of aluminum. Put that in here, moles of aluminum. And so the grams of aluminum were canceled. The moles of aluminum have canceled. 27 and 27 canceled. Oh, that was because it was 1 mole. So 203 divided by 2 is 101.5. So let's keep it to 3 sig figs and round up to 102 kilocalories. Not so bad. Let's do again for another one. Let's do 55.8 grams of iron. That sounds like a random number, but it's not. It's essentially the molar mass of iron. And so heat is always released for this reaction, never the opposite in the thermite process. How much iron do we have here? 1 mole of iron is, check out your periodic table, 55.8 grams. I'm trying to make the math easy for you. And so the grams and the iron go away. And now we have to use our 203 kilocalories per what? Well, let's see, iron in this reaction. Oh, again, per 2 moles of iron. 2 moles of iron. And so the moles of iron cancel. We get the same answer as we did numerically on the first one of this type, in this set. It's still 101.5, or call it 102 kilocalories. It keeps us at 3 sig figs, which is plenty for this example. All right, that was one to do. Let's find another one to just try it out. Here is another reaction that is a little bit different. Let's do the reaction of one of many reactions of nitrogen with oxygen. You can react nitrogen with oxygen, add some energy, and you can get 2NO gas, nitrogen monoxide. So is this reaction endothermic or exothermic? If heat is on the reactant side, that is always endothermic, and therefore it's apparently required. That's why it's a reactant. And so the enthalpy change for the process as written is delta H would be 43 kilocalories. In other words, a positive value of delta H for an endothermic process. And then how much heat what is it going to be, required or released? Well, it's the same for this example, so you haven't changed anything. For 28 grams of nitrogen, so 28 grams of nitrogen. Well, let's guess what? We have to do this per mole again. Well, the coefficient in this example is just 1 on the nitrogen, but we still have to know how many moles that is. So 1 mole of nitrogen, look up at your periodic table, is 28 grams. Well, how convenient. I picked a convenient value for you. And the reaction is going to take or require 43 kilocalories for 1 mole of nitrogen. Well, the answer is 43. So we didn't have to do any more calculation if you realized this was 1 mole of nitrogen. How much is going to be required or released? Well, again, it's still required. If you have 64 grams of oxygen, 64 grams of oxygen, we'll have to find out how many moles. So for oxygen, 1 mole of O2 is still 32 grams of oxygen. Guess what? It's 2 moles. And so we have 43 kilocalories per how many moles of oxygen? Just 1 again. So 1 mole of oxygen. And so that means we have 64 divided by 32 is 2. 2 times 43 is 86. Get out your calculator if you don't trust me, but that's what that one comes out to be. 86 kilocalories. Twice as much because you got 2 moles, not just 1. All right. Hopefully these examples make you realize that the amount of heat is related to the amounts in the equation, and grams and moles are easily related if you calculate them. Now, from the same reaction, let's do another one. If heat is going to be required or released to make some nitrogen monoxide, it's still required. What if you have 90 grams of nitrogen monoxide? Okay, so we've got to figure out the molar mass of that. 1 mole of nitrogen monoxide is going to be how many grams? Nitrogen's 14, oxygen's 16. Oh, 30 grams is 14 plus 16. Again, these are fairly convenient because that's going to be 3 moles essentially. And then it's 43 kilocalories for how many moles? Look at your balanced equation. It was for 2 moles of the nitrogen monoxide. And so we have 3 divided by 2 times 43, and you get an answer of, and my paper calculation gives me an answer of 64.5 kilocalories. Check it out with your calculator. Now, here's another way of thinking about the processes and energy changes. If the conditions were changed, and you can, honestly, with these gases, to allow the reaction to go in reverse, let's not worry at the moment logistically or mechanistically what it takes, 2 of the nitrogen monoxide could be broken down to make nitrogen and oxygen gas. And so if that were the reaction being considered, what would be the value of the delta H? The delta H would now be the opposite of what we saw for the other reactions. So this time it's going to be minus 43 kilocalories since we reversed the process. And heat would now be, instead of a reactant, a product. And how would we rewrite the equation, including the kilocalories in the process? So you put your nitrogen monoxide gas turns into nitrogen gas and oxygen gas. Nothing changed in terms of being balanced. But heat is still on the side with the nitrogen and the oxygen, and we can put our 43 kilocalories here. Again, it still has a positive sign every time it's listed in a reaction equation. Everything in a reaction equation has plus signs in front of it. We don't ever put minus in there. So the punchline for this is to realize that the sign of delta H for the reverse of a reaction is always opposite that of a forward reaction. So the summary of these things is shown on a table here. So heat is always what? Gained or lost in exothermic reactions. It's always lost, and heat is shown in the reaction equation on the product side, and the value of delta H is negative value, less than 0. Endothermic reactions, heat is always going to be gained. It is shown as a reactant, and delta H is greater than 0. Those yellow stars are there because you need to know these, and it helps if you keep them straight. Now, I'm going to continue this discussion in a separate recording, exactly in this spot, but it'll make it easier for someone to interrupt and pick it up in a new spot. So ask lots of questions. Good luck on your homework. See you in class.